Today, we're very happy to have Professor Illah Nourbakhsh, who's an Associate Professor in Robotics at the Robotics Institute at Carnegie Mellon University. He was on leave in 2004 at NASA Ames, where he served as the Robotics Group lead. He received his Ph.D. in computer science from Stanford University in 1996. He's co-founder of the Toy Robotics Initiative at the Robotics Institute at Carnegie Mellon. Today, his talk is on robotics and community for learning and exploration. In his talk, he will describe two major community building projects at the Toy Robotics Initiative at Carnegie Mellon's Robotics Institute. Illah, thank you.
Thank you, Jeff. Well, thank you for coming. And let's see. Let me just begin and jump into it and explain to you what I'll be doing. Actually, let me go back one slide first. So I'm come from the Robotics Institute, and for those of you who aren't aware of what the Robotics Institute is, it's kind of interesting. It's a full-fledged department in the Carnegie Mellon University. So it's a degree-granting program, just like the Computer Science Department, Language Technologies Institute, and Human-Computer Interaction Institute. And it's 70 faculty large. So there's 70 professors in just robotics. So it's a bit of an absurd place. If you find yourself in Pittsburgh, you should visit. There are more robots there than you can possibly imagine. And there are many here who can vouch for that, actually. What I'm going to talk about today are two projects that are partly funded by Google, so thank you to Google, and by others. And they're examples of a direction we've been going into most recently. We have been working on educational robotics, where we're really talking about the educational value of a robot and a person working together. More recently, we've been interested in the idea of educational robotics, where in fact it is through the glue of robotics that we create communities of expertise and communities of practice. So we're very interested in the idea of creating communities of human beings where robotics is really just a motivational technological tool. Thank you, Alec. We have robots. Naturally, a robotics talk without real robots is like a fish without a bicycle, so here's two robots. So I'm going to talk about these two projects. Let me jump right into Global Connection Project, which is the one that has had much more visibility thus far, and some of you have probably heard of that one. Then I'll talk about Telepresence Robot Kit, which is a new project. This is the first real public address on it. And the interesting thing is we have a major release coming up in March where you can actually build your own robot as part of that. So let's start with Global Connection. Global Connection started with a very, very feel-good and incredibly broad vision, right? The idea of getting people to understand each other better, but doing it using technology and doing it by creating community and sharing across people of different cultures. Now, the place that this came from, sort of the thing that inspired us, was the work we were doing on Mars at the time. So the Mars rovers were landing, and some of the people in my group at NASA Ames Research Center were actually helping the scientists. And what they noticed in helping the scientists was that it was the images that were drawing the scientists together and causing really good community building and communication across a diverse group of scientists. So in a way, images were becoming a highly explorable and very interesting phenomena for group education. And the other picture I'll show you, and before I go back to words, is kind of interesting because this is the single most popular picture ever taken during the Apollo missions. This is the last picture taken during the Apollo missions. And the irony, of course, is that this is a picture not of the moon. So the most popular picture taken during that whole set of missions was a picture of us. And so the idea of turning the camera inward, right, of being able to explore and understand the Earth itself is something that's always been magical for people. And this was the beginning of the Global Connection Project. The idea was one way of, and if you read Gagarin's diaries, or if you read Armstrong's diaries, or just about anybody else who's been in space from either side of the fence, what they say is that once they're in space and they've orbited the Earth, they see the Earth in a different light, and they feel for the oneness of the Earth and the idea that political boundaries are somewhat transient. So one idea we had was, okay, so maybe we should just fundraise and take everybody that makes political decisions, say, and send them into space for a while, have them orbit the Earth. And that might actually increase global understanding significantly. Now, there's a downside to that because we computed that the amount of carbon monoxide and ozone that you release by doing that would accelerate global warming significantly. So that's actually a bad idea. So we can't put everybody in orbit for a while. That's a bad idea. So the next thing is, can we create visualization tools that help people to understand the Earth better by giving them a new, more explorable view of the Earth as a whole? So we wanted images to be the center of this, and we launched 3 specific initiatives last year which have paid off pretty well. The first 2 have paid off really well, and I'm going to tell you about the motivation at the bottom there. By the way, I'm going to talk fast and go through the slides quickly because I want you to be done by 3:50 for obvious reasons. So first of all, create content. what we wanted to do is start by having really compelling professional content, something that people could really get into because it's professionally done content that they want to see. Throw that in a spatial browser, in a format that they can see it and explore it and learn more about the world through it. And that would be kind of a catalyst for learning more. Second thing is we wanted to create a technology for hyperrealistic imaging. So in a way, if you think about digital cameras and where they are, we wanted to turn the gain way, way up on that, so that you have far better spatial resolution, far better temporal resolution, in other words, being able to go back and forth in time, and much, much better dynamic range. So you can have pictures with lots of resolution and yet the ability to see across a very broad range of brightness values. And then third, we wanted to start to build specific communities and create communities that are self-sustaining around all of these topics of interest. So those are kind of the first three steps. And this is here because if you think about the driver behind this project and the other project I'll tell you about, Aristotelian passions sort of start with imagination and creativity, the idea that what drives humans and makes them human is to imagine and to wonder what the world is like. Well, there's two kinds of imagination that Aristotle talks about, right? One is imagination of the natural world, imagining and wondering what the world is like and what's cool about the world. And the other one is imagination of the creative world, imagining what you could do to the world. How could you change things? How could you invent something new? We're trying to do both of these. And so this first project tries to hit on the question of wondering about the real world. So what we want to happen to people and the way we want communities to build is we want people to wonder, right? Because you create tools that help them become wondrous about how rich the world is. And you want them, by using those tools, to explore the world and discover things that they didn't know before. And you want them to discover things that are so compelling and rich and interesting that then they feel compelled to share. And so that's kind of one trajectory to a self-sustaining community. You'll see a different three sort of tuple in the case of the Telepresence Robot Kit project. So the project we did, long story, very short, is that we talked to National Geographic and got them excited about it. We talked to Google Earth, or Keyhole at the time, and got them excited about it. And thanks to many, many, many people who said yes and helped out and provided funding, we managed to take hundreds of articles in Africa and geocode them onto Google Earth for Africa. So that when you spin the globe in Google Earth to Africa and zoom in, you can see little boxes. And of course, when you click on the boxes and zoom in further, you can see articles that are on National Geographic Online. And so those leads to articles. The other thing we did has to do with these little red dots. And this is kind of interesting. Mike Fay is an incredible guy. He's raised actually billions of dollars for world hunger relief now. He flew a Cessna 182 over Africa and collected about 90,000 images with GPS coordinates that were rough. Not very good because they were coming asynchronously off a GPS receiver. Well, we took that data and we geocoded it as well. And a lot of that is now available too. When you zoom in on those airplanes, you'll see his pictures. So you'll see things like, oh, this is interesting. This is the only structure that's man-made that is visible from space, which is a giant conveyor belt. It turns out the Great Wall is not visible in space, as those of you who know about some websites have found out. And you'll see things like spice trading bars, where people are actually trading spices and looking up at the airplane, wondering why there's an airplane flying overhead. And the level of zooming is pretty astounding. If you zoom into one of these airplanes on Google Earth, you'll see a super resolved section within Google Earth, right? And that super resolved section is there because our team did such a great job of lining up the high resolution image with the Google Earth satellite data. And when you zoom in, of course, you see really good data like that. And if those of you who've played with this know that you can get to the point where you can see people carrying a baby on the back, walking with a shadow cast by a sunset moon, a sunset sun. Setting sun, that's the word. Well, this flyover stuff led to somewhere interesting, which is that the technology that was developed to make this kind of thing facile turned out to be very useful when you were starting to talk about disasters. And so when the hurricanes Katrina and Rita happened, and again when the earthquake happened, it was a great time, and we were very lucky to be in a position to actually take thousands of images that were much more recent images post-disaster and overlay them onto Google Earth. And that's turned out to be a really useful tool. These are examples of some maps that we've overlaid onto Google Earth that are recent maps and helped disaster relief workers and logisticians in Pakistan plan routes and figure out which villages they can go to and how. And I guess there is a story I wanted to tell about disaster aid that very, very briefly. The story that's interesting to me is that there was real demand. So federal agencies were coming after Google and then coming after us and saying, look, please do this overlay for us. And there was supply. It turns out there was a whole network of people who wanted to be part of a community helping with disaster relief. So a lot of people who were looking at the television, reading the newspapers, learning about the disaster, were reading this going, I want to help in some way. How can I possibly help? And so it turns out a number of people were actually acting as clearinghouses collecting data from various sources and creating a fusion of data from several sources, such as a map from here and a word description of a problem in a specific village, and then locating that using Whirlwind or using Google Earth or any other tools. And so, and the last thing but not least, there is a set of eager technology that we've noticed. So just as an example, very recently we've been approached by the biggest cell phone company in the world. And what they say is, we have, and I've forgotten the number now, 15 million users who have video cameras and very, very high bandwidth connections. How can we make sure that whenever there's a disaster, anybody with those cell phones can snap pictures and overlay them automatically into your system? Because we can triangulate within 10 meters using the radio towers. And it's a really nice idea, right? It's something that we can definitely do by doing some really interesting image work on the images that they snap and the satellite images that we have. So disaster aid seems to be one really good example of a community that has been born completely asynchronously, chaotically, and will definitely last. Now, those were all sort of detours from the original task, which was we wanted to use images to explore, but we wanted to create tools so that images are hyper-realistic. So we wanted images to be, in a way, much more realistic than they are today. So let me tell you, kind of pitch you this idea and then show you the results. So the idea is, we want images to contain so much information that, as I showed you that kind of Aristotelian passion direction, we want your act of looking at the image to be filled with wonder. And we want you to spend so much time with the image that you discover things in the image nobody else has seen yet. So imagine an image that's so rich that it could do that. And then we want that discovery to be the thing that leads to sharing, to the desire to share it with other people. So that's what we want to do. And the thing that we started doing, and again, like everything I'm talking about today, none of this is actually crediting me. This is all the students and other colleagues that I have. I just get to talk about it. Gigapan is this really neat thing that Randy Sargent came up with on our team. So the idea is it's two very inexpensive stepper motors that in a very clever way are micro-stepped using a very inexpensive chipset that's off the shelf. And the result of this is you can take any old digital camera, attach it to this base, and then over a USB connection, the computer commands the USB camera to fully zoom in optically, and then take hundreds of pictures and stitch them together. And do this many, many times. So if you can put this on a tripod, put it outside, and do this over and over again for the period of a year. And we have done this. And what's exciting about this is the chipset that we have, the board that we have, fabbed and evaluated, and the stepper motors, and the mechanism itself, all add up to about 40 bucks. Now, if you look at Michael Jones' Gigapixel Imager, which he has 2 or 3 of here at Google, those are from U-2 spy planes, and they each cost about $12,000. And there's very, very few of those in the world. So the idea here is, this is also a Gigapixel Imager. It's not as high quality as that, but it's a lot less than $12,000. And we can publish an open recipe so that anybody can build this. And that's kind of exciting. Let me show you a quick demo just to give you a feel for what it means to have this kind of explorable image. So this is an example of an image that's taken by this thing. And this is pre-stitching. So there's no stitching technology yet that's run on this. And you can see that there's a lot of data there. Explorability, in a sense, means that you have sort of hyper-resolution. What I'm interested in is the idea that you can not just zoom in, but you can zoom in to a degree that's kind of unheard of with a regular picture. This happens to be about a 1 gigapixel image. And so you can really go in and see the leaves here. And you get a level of resolution that's kind of fun. So you get the idea with that. And doing that in all different directions, even in this backyard of Randy Sargent's in Palo Alto, is kind of fun because you'll find blueberries and such. Now, remember I talked about temporal resolution. I want the idea that pictures become explorable in space but also in time. And so if I can get over there, let's see, my screen, I have one little example to show you of temporal resolution over the course of about 9 months of data. Boy, this is hard without looking the right way. I'm playing a mapping game here. There. So when I show you that lemon, now let's roll back in time. And so what you're seeing is the passage of time in reverse, and you'll see the lemon become I guess it's not called a lime, whatever you call an unripe lemon. A green lemon. And it's kind of fun because as you go through this with greater detail, with greater temporal resolution, you end up seeing some morning glory weeds. You can see them right there in the corner, top right. And then the neighbor pulls the weed out and the leaves all of a sudden wilt. You see that on the top right. Anyway, that's the kind of thing where we think it gets exciting to be able to explore and to be able to put a camera like this into all sorts of places. You can probably imagine for yourself several places you could put a camera like this right now and collect really interesting data. We're working on the stitching technology now. It turns out you need to do some stitching that's a little unusual compared to the kind of stitching people normally do to make this work right. Mainly because we want it to work really, really quickly. We want people to be able to do this with massive amounts of data. So that's the end of a brief introduction to global connection. Let me tell you what we're up to next so you know how to track this. For those of you who've been at NASA before, and there's several in the room who were at NASA before they came here, you can appreciate how hard this is, but we got a Space Act agreement on this, which is kind of cool. It's this collaboration now between National Geographic, Google, CMU, and NASA that officially allows NASA to give us resources, images, data, servers, and people. So that's kind of neat, and it's for free. One exciting thing that's happening is we've done Africa, as you can see if you go to Google Earth today and spin there. And by the way, something that blew us away was the idea that Michael Jones and Alan and Matt and everybody on Google Earth team made it the default layer on. So everybody that has Google Earth immediately when they spun to Africa could see the stuff, and we're really proud of that, and that's just a really neat thing. But the good news is that's being expanded. So you'll be able to see other parts of the world geocoded, and you'll be able to see other kinds of data other than National Geographic data geocoded. The other thing we're trying to do is we're trying to launch an international infrastructure for disaster visualization. It turns out the disaster stuff has worked really well. And you know, we had a period of time where a major flood hit Pittsburgh, the building in which our server is housed, which is serving, I think, 1 terabyte of this data to international relief workers now, a day. And it turns out that this was a big problem because we started getting phone calls from Pakistan. And that was kind of neat, right? Because that tells us, okay, they're actually using this stuff. So now we want to go after the idea of creating infrastructure for this kind of disaster visualization. The exciting thing we're doing is, hopefully in about 3 months, is we're going to do an open recipe release of Gigapan so that you can build one. So there'll be a list of digital cameras that are supported, all the source code will be there for the driving it, and the stitching software, and the directions for how to build yourself one by going and buying parts from various hardware stores. Then we're going to give a bunch of Gigapans to photographers. We actually have a bunch of Gigapans right now. We have 15 and we're building 50 more. So if you're a professional photographer and you want a Gigapan, talk to me. And then we're going to create a bunch of different themed activities that create focused communities, just like the disaster relief community. That's global connection. Now let me tell you about the other project. And what you're going to see is how the other project is kind of a complement to that project. That project is about wonder and discovery of the natural world in a way, and cultures in the natural world. This project is about invention. And here's why we're doing this project. The problem that exists, first of all, this is kind of neat. Science and engineering are almost dropping in the US, and only in the US. So welcome to the one place in the world where science and engineering are becoming less desirable every year. And this is for real. The data here, by the way, is from ACR and from the Girl Scouts National Report, which is an excellent document, and from the CRA recent report. Now, there's a women problem in the US. As you may be aware, we have a very small proportion of women in technology and engineering fields. And in fact, in CS, they're actually decreasing. So this is interesting. This is one of the only areas in engineering where the amount of participation for women is going down. And what happens, I'll let you read this yourself, but what happens in narrative form is that some of the analysis that's been done in this area indicates the following. The concept is that women are really excited about technology insofar as technology is a tool for something that they deeply care about. Men seem to be satisfied often, this is rash stereotyping, of course. Men seem to be stereotypically happy to invent and create technology for the sake of the technology itself. And so a lot of time what will happen is in middle school, women are actually perfectly happy using technology, such as instant messaging and blogging. But by the time you get to high school, they're asking, well, what is this for? If I'm going to take Intro to CS, why bother with Intro to CS? What kind of tool is that for the things I care about? And so what we've been working on is an idea that, in fact, what you need is the ability to create a sense of purpose for the technology. And robotics turns out to be a really nice way to do that, because it's a concrete, grounded object which you can actually program to do interesting physical things with you. It can interact with your sister, it can interact with your brother. It can take environmental readings for you and report on the pollution levels over the course of the day. So it's a sensing and actuation device. And when I say robot, I mean much more than a Mars rover-like device, but in fact, any device that senses from the real world and actuates into the real world again. So we've done a lot of testing now. We've got more than 200,000 children using these robots at museums across the world. And the results of those testings have been somewhat promising. The things we've seen that are interesting in classwork with these kinds of robots is gender retention. We're having people come in with statistically significant reports of lack of confidence in using computers, and the rate at which they increase their confidence in using computers is statistically significantly higher than the men. Why is this happening, you might ask? Well, what's happening, and this is kind of funny, but in many of these courses, the women are programming the robot to do a task, such as navigating the building and getting somewhere and delivering a message to somebody. Well, the way they do it is they talk as a team, good at talking. They come up with a solution, they run it, and as it fails, they run it again, and they look at it and they scratch their heads and psychoanalyze the situation and do better, because they understand how the robot is interacting with this complex real-time world, the real world. What do the boys do? Well, they program the robot together, they run it, and as soon as it turns the wrong direction and crashes into something, they stop it and change the code in 3 places and then run it again. So they just keep trying to change the code to see what will happen. And although this may work for simple computer programming assignments, it doesn't work in robotics because the system is too complex and too deeply embedded in the physical world. And so observation and the ability to take on the robot's point of view turn out to be incredibly important. So this is not really gender specific. And the point is that you want everybody who doesn't have a sense of empowerment over technology to feel much more empowered toward technology. But having said that, just looking at statistical analysis of words, when we interview people and have them tell us, what do you expect to learn this week? When you ask them this question in, say, a computer science robotics class, they report programming and mechanism, which makes a lot of sense. After all, robots are computational systems, programming, and mechanism. Week after week, if you ask them what things they learned that week and code that, what you get is teamwork, problem solving, identification with technology, robot point of view, far, far higher ratings than you originally would have expected. This is exciting because this means that there are lifelong learning lessons that are to be had in interacting with this particular robotic complex system. And so it's much more than just learning how to use a robot. It's about learning how a complex system works and learning how to put yourself in its point of view. So that's the introduction. What we're doing with Turk, I'm doing good, okay. We're doing with Turk is trying to create a new way for throughout the educational pipeline, middle school, high school, community college, college, and adult, a new way for people to be creative with embedded technologies. So we want you to be able to dream up something that you want a system to do that has sensors and actuators, and to be able to build it with great ease. We want it to be really easy for you to build this thing and realize your vision and then share it with others. So it's about community building, but it's also about you being able to do some absurdly cool, creative things that you can't do today unless you know a whole lot about PIC programming and about sensors and about how to connect something to the internet, say. So if you think about the Aristotelian passions, what we're getting at is the complement of wonder, ingenuity. And ingenuity, the root of engineer, is all about the idea that you start with creativity. You start with the idea that I want to do something different than what I can do today. And so first of all, I need to give you an intuition for what's possible. What could you do that's creative and different from what you can do today? Then I want you to be able to actually realize it. So it has to be easy enough to use that you can actually build it and then share it. And so what we're expecting is you can create a different kind of community. Now, in a way, this is like saying we want to create the ultimate Lego Mindstorms kit. Yes, Lego Mindstorms just announced a new kit, and it has the same problems the old kit had. It doesn't have vision, it can't see the world, and it's not wireless. So what do we really want to do? We want to create a Lego Mindstorms kit that you can build with, but you're not building out of Legos, you're building out of stuff that can last. So if you want to make something that lasts all week or all month, you can. And we want it to have vision, we want it to see the world and react to the world appropriately, and we wanted it to not have a ceiling. We want you to be able to get as sophisticated as you want on it. So this is a very, very ambitious goal. And there's a lot of thrusts in this work, and so we have a very large consortium of funders and people who work with us on this. The first thing we've been doing for a long time now is a national survey of computer science 1 courses, actually 0 and 1 courses, across the US, and a survey of all the textbooks that are used, or rather the top 15 textbooks that are used in Intro to CS. Another thing we're doing is developing a new kind of electronics package. The project's called Twerk, so naturally the electronics package is called Quirk. The electronics package is actually about to be released, so that's something I'm going to spend a lot of time telling you about. Another thing we're doing is creating a reference design library. It's a set of recipes, like a cookbook on the web. The recipes are step-by-step instructions for how you can buy off-the-shelf parts at places like Home Depot, and in about 4 to 5 hours build a robot. It's a series of recipes that are reference designed, so that once you've done 2 or 3 of these, you can be very creative and feel empowered about building any kind of robot you want. Again, The word robot is used loosely here. I mean any device that senses from the physical world and actuates based on that. And we're doing a lot of curriculum design and then pilots throughout the educational pipeline across the country. So the national survey, just to show you a feel of spread, those are the schools across the country that we're surveying. In terms of recipes, we're doing a lot of different recipes. Right now we're doing test builds of students at CMU. So we're taking students who don't have mechanical aptitude and having them actually build the robots. And we're having them build this robot right now, which is the base of a large fingered robot. That's about a human height robot. It's fun to have them build these kinds of robots because we do interviews with them along the way. And what we're discovering, which is exciting, is that during this 5-hour project of building using just hand tools, they're actually going from a, I'm not sure I can build this, I've never built something before, to at about hour 2.5, this is fun. I wonder if I could build something else that uses this mechanism and does in such a way. That's exactly what we want to see, and luckily we're seeing that. Really, really simple for those mechanical people amongst you. For instance, you want the gear train to be easy, but you want to teach people something about mechanical elegance and simplicity. So it's a friction drive mechanism. There are motors that have an eccentric axis. So you just put a hole in a piece of wood, and now by spinning the motor, you can offset the axis exactly the right amount to get the right thrust against the wheel. So really simple things like that. Now let me tell you about the controller, and this is the latter part of the talk. I'm trying to finish early so that before 3:50 people can actually ask some questions. So the challenge, and this is the hardest part, okay? Just be clear. Curriculum is really hard. Putting this into the pipeline is hard, but the good news is we have friends across the world that are interested in this kind of thing, if you could pull it off. But how do you build a really affordable processor? You want it to be 32-bit, you want it to have floating points so you can do lots of cool things on it. You want it to be wireless right out the boot, and you want it to have a webcam on it. Obviously, you want digital and analog inputs and outputs. Now it gets a little tricky. We want you to be able to take any motor and hook it up to the system. So that means it's not good enough for you to have to use a Pitman motor that's $120 with a special encoder. We want you to be able to buy a drill from Home Depot, take the motor out, and just use it as is. No encoder. And that's possible using something called back EMF that we've been working on. We want you to be able to control lots of servos so that you can make a face if you want to and have the face smile, or a multi-legged insect that walks. And we want the thing to be incredibly power efficient so that it lasts for 12 to 15 hours on a charge. Okay, and you want it to be about $100 bill of materials. So that's the goal. One way you could go about this is you could say, okay, cool, we're going to use sort of a commercial off-the-shelf approach of a mini ITX, sort of an embedded PC. The problem with that approach is that's not a robot controller, that's just a PC. So even if you do this and you have your mini ITX, you still don't have analog inputs and outputs all done. You can't control the servos without putting massive numbers of timers on this thing. And you certainly don't have the back EMF control or the power switching regulation system or the MOSFETs that amplify for the motors. So you're missing a whole bunch of things that allow your box to connect to the physical world. And that's the part we care about. So first of all, I'm going to argue an ARM is much more attractive than this mini ITX kind of solution. It turns out ARM 9 cores are very good. They can run Linux. The entire ARM 9 solution we have is $50. So that's an ARM 9 running Linux with everything else that you need except for the robot input and output. And it consumes far less power than the ITX. So the idea of running all day is entirely possible. But you still need the I/O.
What's ARM?
ARM is the processor in cell phones. It's a microprocessor. So, yes, Peter.
What if you assume that they had a laptop and you just put Wi-Fi on it and the computing on?
We are assuming that many people have laptops, but we want the robot not to have their laptop on it. So unlike evolution, we don't want you to risk your laptop on your robot. We want a robot that's so cheap that it can talk to your laptop and anybody else's laptop. In fact, let me spin you the story of how you use this. I didn't say this part, and this part's kind of important. So here's how the average person, here's how Alec will build his first robot. He will go to the website, and he'll choose amongst the recipes. He'll order one of these black boxes. This costs about $200 retail. So he'll order the black box. He'll go to the website, get the recipe, build it. It takes about 4 hours. Once he's built the recipe, he plugs in the plug into the black box, turns it on. Once he turns it on, green light comes on the black box, and at this point he goes to a web browser and goes to our website at CMU, and he can now see his robot, he can control it, he can write a iconic program for it, or he can just drive it around teleoperationally. So the idea is that in fact the thing is on the internet, but it's using a microprocessor that's very low power, much longer than your laptop will, but you can talk to it from any computer anywhere. So that's the goal, and it's pretty exciting if you can actually pull that off. Well, let me jump to the solution. What robots really need, in a way, is something that can do the closed loop motor control, something that can deal with the power management. And the problem is, when you think about what a robot does and what a robot contains, the mistake people make is often they end up doing a lot of what could be done in hardware, in software, for the robot's sake. And this is unnecessary and expensive. So the solution we propose is you use an ARM9, which is much less powerful than the Mini ITX, and you add a robot ASIC. Now, what's a robot ASIC? What's a great ASIC for a robot? The answer, the thing that is interesting about robotics, is that we can use something that is really customizable as you reconfigure the robot. So you don't want an ASIC for a standard robot, but rather something that can customize to any robot that you build. So our solution is an FPGA. So our proposal is, in fact, if you can have an FPGA that implements all the robot-specific options and, in fact, is the thing that you, in real time, can reconfigure as you need to, as you change the number of motors on your robot, say, then you have incredible flexibility. And it's about $5 in quantity, so very, very cheap. In fact, better than that. Xilinx has donated them all to me, so I have a lot of Xilinx FPGAs. And just to show you an example, this is something that Rich Legrand did at Charmed Labs with my help. And this is the launching off point of what we did. This was the Game Boy robot controller kit that had a Game Boy processor and an XPC, and you plugged in an FPGA into the Game Boy. The FPGA took care of all the robot I/O. So it had the watchdog timers, it did the servo controllers, and it had the UARTs, Bluetooth interface, all those good things, all on the FPGA. What we're doing is this. And the good news I can report today is this is actually working now. So I'll show you how much of it is working, but it's an ARM9 with floating point. It's got the 300,000 gate FPGA from Xilinx. It's got USB 2.0. Wi-Fi and webcam is a kind of a story that's worth telling. Wi-Fi is easy. There's several Linux patches that make Wi-Fi work just fine on an ARM9. Webcams is a tough one. If we're going to put recipes on the web, right, we want the recipe to say you can use any of these 5 webcams. But if you look at the webcams that are on SourceForge that there are patches for Linux, they're all webcams that are end of life. Because they've been around a while, so people could actually hack them. So we talked to Logitech, and we got from Logitech copies of the cameras they haven't sold yet. So these are next year's cameras from Logitech. Well, this year now, it's 2006. So they'll be on market in a couple of months. So we got these from Logitech last month. And then we found one of the hackers, a very nice guy named Michel Zar in France. And so he agreed to roll the patch for us for these webcams. So we gave him the webcams, gave him the processor board, and he rolled the patch for us, which was really kind of a neat story of collaboration across the ocean. And there's lots of other good stuff on this. It does MP3, of course. Got to do that these days. It's got 12-bit analog inputs. It controls 16 servos. It has a switching power supply into which you can plug in any number of Radio Shack 7.2-volt battery packs. And it switches between them appropriately for the motors and everything else. And right now, we're at about $112 bill of materials. So that's exciting. And that includes enclosure and manufacture. It's got temperature sensing, and it's also got current sensing on every line through the FPGA. So we can tell exactly how much current is being drawn on what motor, which is really fun. So as of last week, it's running 268. We've got back EMF working with 12 and 24-volt motors. I'll be right with you. And we've got wireless up and running. So we're very close. And that's kind of an exciting point, because if you can get this thing, if it's really 110 BOM, and if Rich agrees to sell it for about 2x, so if we can get this out the door for, let's say, $250, then that means you're buying something for $250 that once our firmware is done, you can literally build various robots, plug in all the wires, turn it on, and now go to a wireless connection and talk to it. And what's more, it can do vision on board. So you can really have a kind of an intelligent robot. Your question?
Do you need hardware to program the FPGA, or can you do that from the ARM9?
You can do it from you can do it right from the ARM9. Yeah, you can reconfigure right there. So here's the next steps on Turk. There's going to be a tech report this month on the Intro to CS curriculum evaluation. And the good news, by the way, on the textbook and on the teachers that we've interviewed is that they all seem to agree and recognize that Intro to CS sucks, and that they want to change, and that they change textbooks every couple of years. So changing isn't particularly hard bureaucratically speaking. In fact, there's an interesting thing that they point out. They themselves point out. They say, well, our exercises are things like write the Fibonacci sequence, write 99 bottles of beer on the wall. And our students don't seem to connect to these, especially the women. And we go, huh, that's exactly what the Girl Scout report says. Intro to CS assignments, which are so incredibly abstract, are not that exciting for people. And I find that stunning that so many of the assignments are like this in so many of the textbooks I see, when in fact we have the internet, we have sound, we have light, we have so many interesting ways to imagine writing Intro to CS assignments that connect your process to the outside world and read interesting values. We're doing a Chatham College deployment this month. We'll be at 6C. We're running a workshop and a Birds of a Feather seminar there. So we'll be introducing this to a whole lot of computer science professionals there. The public release is in March. So hopefully in March, if you go to the Turk website, you'll be able to download code and download a recipe and go to your local Home Depot and build one. Home Depot is a group we're talking to right now because they want to be one of the sponsors too. They'd like to make kiosks in Home Depot where they accumulate all the various parts from Home Depot that you need to build one of several robots. So that'll be kind of fun because you can go there and buy all the parts and Bob's your uncle. We're going to also be running the Grace Hopper Saturday workshop. So if you're going to the Internet Board Foundation's Grace Hopper series, we'll be there and we'll be doing a full clinic on this and giving away Turks there as well. And then we'll be launching at 5 schools in September. And we already are running curriculum at Columbia, CMU, and Verona. Carl DeSalvo is an interesting fellow. He's a robotics and art guy. He's going to be going to art workshops. Art, as you may know, are serious early adopters of technology. And so the art community is really excited in this kind of thing because you can imagine what they can do with something that's internet connected and controls all their motors for them. And last but not least, I'll tell you very briefly about these two things. They're in brackets because we're still in the middle of getting funding for those. The good news is the rest will happen, so we have enough funding for it. But those two are interesting. If you look at what, 60 seconds. If you look at what girls undergo in middle school versus high school, in middle school it's about identity of self. So they're really interested in the question of who am I? And in fact, journal writing and blogging are somewhere that people put a lot of emphasis. If you look at high school, it's my identity with respect to my community. How can I be a member of a friend group, and how can my friend group have impact on something I care about, like the environment, like politics? So what we're doing for middle school girls in 10 seconds is we're creating a robot diary system. So it's a set of recipes for Home Depot that build a robotic flower. As you write your blog or journal, the emotional content causes your flower to do various kinds of choreographed dances, play music, and do light shows. And you can share this with your friends. You design all the choreography, and you design how it shares with your friends so that they can see how you feel today. For high school, we're doing a SensorNet program. So the same black box becomes a sensor that reads carbon monoxide, ozone, and a number of other fluids. And you connect these in a network in a city, and you're challenged not only to fuse the data together, but to create public pieces of art that are kinetic sculptures that demonstrate to the public what's going on with environmental quality in their area. So that's kind of a fun idea too. So the last slide is the thank you slide. All the real work on Global Connection is done by Randy Sargent and company. All the real work on Turk is done by Emily Hamner and company. And we have a lot of collaborators right now around the country, and the funding, as you can see, comes from diverse sources and keeps growing, which is great for us. Okay, thank you for your attention. You have 2 minutes before 3:50, and you're welcome to ask questions now. Thank you. I forgot to tell you one very important thing. March is when the Turk gets released. Before March, these are here now. These are personal exploration rovers that are programmable in the same way that Turk will be programmable. So if you want to program a robot for any reason whatsoever, these have cameras on them, they have rangefinders, they move 4 times faster than the Mars rovers on Mars. So they're even faster than those robots. These are per turbos, technically speaking. We've provided them here to Dan Clancy, so he has access to them here. And if you want to program a robot, just email me and we'll get you set up with one of these, and you can program away. You can take it home and program it all you want. And it has wireless on board, everything. So you're free to use these. They're on indefinite loan to Google. Yes?
When you say they'll be available in March, what's going to be available?
What will be available in March is you'll be able to buy the controllers from charmedlabs.com and probably a couple other companies. You will be able to go and download recipes that show you what parts to buy to build robots, and there'll be at least 3 recipes up. Robotic flower, which is kind of a desk art piece. The QuirkBot, which is a very simple robot enclosure that fits onto the processor itself. So the processor becomes a desktop robot with a camera on top of it. And ShenBot, which is a tallish robot with a prismatic arm that can push buttons in an elevator, so you can use an elevator when you're not there. A very useful thing to do, right? With a large 2-wheel platform on the bottom. And that's more of a human walking speed style robot. So our litmus test was we want a robot that's good enough that it can use an elevator. Because that requires simple manipulation and vision. And if you can teleoperate it and do that, that's kind of fun, right? Because you can travel around and visit people when you're not there.
How much would something like one of those cost?
I can build 40 of these at a time for $160,000. So these are much more expensive. It's $2,000 a piece, right? $4,000 a piece. This is the problem with robotics. In general, robots that are sophisticated cost a whole lot. The amazing thing is the QuirkBot, the parts will cost you $80 plus the board, which will cost you about $250. And yet it's got vision and it's wirelessly connected to the outside world. So it's because of the ARM9 and because of the FPGA that we're achieving such a price. These have a Stargate processor in them that Intel gave us for free. So Intel gave us 160 Stargate processors. That's why these exist. But that Stargate processor is it's an ARM. It's an ARM core, but that Stargate board alone, which you can buy from Crossbow, costs I think $900. And that's without the power modulation. And of course, that's just a board. It doesn't have the robot stuff on it, right? It doesn't have servo control or motor control. Yes.
So you mentioned Lego's Mindstorm earlier. How compatible is the Lego's Mindstorm? Are you making any effort to?
Once they've claimed that this time around they're not going to be secret. They're going to be open, right? If they give us an open architecture, I will make this compatible right away because it's a no-brainer. That way people can also build out of Lego and control it from the Quirk controller instead of the Lego Mindstorm's controller.
They're really interested in doing educational stuff.
Oh, yeah.
MIT's already using them. A lot of places are already using them. So you can take your Lego robot and pick one of these on.
Yeah. You basically put your Lego robot on the web with camera. Yes?
So you mentioned that the CSO lens looks mostly stuck. What are you going to do about fixing that?
There's one good one we found. There's actually two good ones. One is called something like a head-on approach to CSO1. It's by two researchers at Sun who wrote it together. They've written a million books together. This one's the best one. One thing we're going to do is approach them and see if they're willing to write a new version with Turk in their book or on a companion lab volume. But even if we don't do that, what we're going to be doing is publishing on the web a series of exercises that go with various CSO1 books. So we've looked at the modules that exist, and it turns out intellectually the presentation material is pretty consistent. So we can very easily come in a surgical way and propose certain exercises with Turk along the way that we think will make it a much more exciting class, especially for women.
Do you consider doing like a wiki-vote approach to really full?
We've considered it. We want to start with something surgical, and then if it catches on, if we get good evaluation results with our educational work, then yeah, we want to do the whole thing. That'd be ideal. But we should find a CSO1 author to do with that. That's the best way to go. Okay, thank you for your attention.